Hello, statisticians, back here with our second sampling distribution lesson. This one's going to focus on the mean side. So the progression here is the first sampling distribution was kind of the general breakdown of what a sampling distribution is and why we have them, along with bias and variability. In the first lesson, I touched a little bit on p hat and p, which are the proportion side of sampling distributions. And in this lesson, we're going to focus on the other one I mentioned, which was x bar and mu. So we're looking at just the mean side. So this is mean heights, mean weights, mean distances, mean amount of money, mean score, things like that. So we'll take a look at that. So first of all, what things we want to know, how to determine the mean and standard deviation of a sampling distribution, which we'll cover first. And then we are going to talk a little bit about the central limit theorem. Okay, and the central limit theorem is perhaps our most important single theorem or definition or anything that we have in AP Stats. It would be the equivalent to the Pythagorean theorem in geometry or the quadratic formula in algebra. Central limit theorem is extremely valuable for us and is a good thing to know and what it accomplishes for us. And then we're going to calculate a couple probabilities at the end along with describing some distribution. So first of all, the parameters that we have in this lesson are mu and sigma. Okay, mu is the population mean, and sigma is the population standard deviation. So you will see both of those, and then we'll talk about x bar, which is the sample mean. What we won't talk about in this is S, which is the sample standard deviation. That will actually not show up here in this lesson, but the x bar and then the mu and the sigma, and again, being population values, and with us not really looking too much at population data ourselves in terms of putting it into a calculator or a spreadsheet or anything like that, more often than not, these values will be given to you. And almost every time they'll be given to you. So, so plan on those values being something that is referenced in a question. And again, what they would say is the mean and standard deviation of, and they would list some population of Minnetonka High School students, of Minnesota residents, of seniors at the high school, rather than saying of a sample of 30 or of a sample of 50 or of a sample of 1,000. These will just reference mean and standard deviations with no reference to sample. The sample will come in when we talk about statistics, and then N is going to be that sample size that we talk about. So first of all, sorry, a little formatting issue here, but this idea, so suppose you draw many SRSs from a population and you create a histogram, and what happens again is you get this histogram where these are all X bars. Okay, so if this is height in our school, again, it might look something like this, where these are all the X bars from a bunch of samples, again, millions of samples, but here's just an example that has, we'll put 10 X bars in there. And again, the idea is to get that shape that's roughly normal. Well, the mean or the center of this histogram, as you can see here, the center of the one I drew would be at 68 inches. And what that is the mean of the X bars will equal the mu, and I referenced this a little in the first lesson, but what this is saying is the mu of the X bars means the average of, if you just typed all these X bars or added up all these X bars and divided by how many we have. So for instance, if you did 67 plus 67 plus 67 plus 68, 68, 68, 68 plus 67 plus, excuse me, plus 69 plus 69 plus 69 and divided by 10, that would be the mu of the X bars, okay, for all millions of X bars that we get. Well, what's going to happen in the end is those will end up equaling the population mean. So what we're saying is if you took a million X bars, the average of those would be the same as if we just went and asked all 3,200 students, how tall are you? Which we wouldn't do, but that's where the sampling distribution idea comes in handy. So the mean of all the X bars will equal mu. That's the center of the distribution. Okay. Now the spread of the distribution is actually a result of the relationship between the original standard deviation, which again would be given to you. Okay, so that numerator would be given to you, and they would also give you the sample size. Now, what's important here is to, again, keep the notation, okay? You do need to get used to writing this notation. You can't just write if sigma is 10 and n is 100, you can't just write 10 over root 100 without any reference to what it means. So the sigma of the x bars equals sigma over root n, which is, and then you'd write whatever, 10 over root 100, which is equal to 1. And so that would be the notation there. On the center side, the notation would simply be mu of the x bars equals mu, which equals 68 inches. Okay, something like that. And so the notation is as important as the values, and the notation is actually given to you. So on the formula sheet, you get this notation. So keep that in mind. Now, the central limit theorem, again, this is one that you're going to want to keep near. And I'll just read it here quickly as you're reading it. The sampling distribution of the means from any population whatsoever, meaning could be skewed right, skewed left, not skewed at all, really, really badly skewed, whatever it happens to be, could have outliers, whatever it is, will be normal provided the sample size of the individual samples is large enough, which we've denoted is n being 30 or more, and that will cover all shapes. So what that's simply saying is even if the distribution looks like this to begin with, as long as we take a bunch of x bars and just graph the x bars will look like this. And what might happen here is on this one, here's the mean right here, and let's just say that's 50, whatever, $50. Well, that means here is $50 on this one. Okay, so if you overlaid the sampling distribution would look like that. Again, it's the same values, it's just in this situation, we're looking at individuals where n equals 1, and in this situation, we're looking at n being 30 or more. Let's just say it's 50 here. So that's the importance here. And what the central limit theorem is it's really about the shape, and it's about assuring, not, you wouldn't want to say normal, but you would say roughly normal or approximately normal. It's very particular to not just say normal, because that suggests it's perfect, and it's not going to be perfect, but it will be close to perfectly normal. So we'd say roughly or approximately normal. Here's just a picture of various distributions going through this process. So you can see one that's already normal just gets skinnier. Okay, that's the variability going out. Okay, so as n increases, variability decreases. That's what's happening there in that first one. In the second one, it started out skewed, and you can see with n equaling 3, it was still slightly skewed to the right, but better. With n equaling 5, again, it was still very slightly skewed to the right, but better. By the time n equaled 20, it was roughly normal. Uniform. In this case, by the time n equals 3, it was roughly normal. Irregular. You can see at 3, it didn't look great yet here, but by 5, it does look pretty good. And what this is hitting on is the idea that it doesn't always take 30. It might take 2, it might take 10, it might take 25. But what we know about 30 is it doesn't matter how ugly the original distribution is. Okay, it could look like that. And we can, as long as n equals 30, we are going to end up down here getting to one that's roughly normal. Okay. To ensure that our sampling distribution is normal, there are two important factors, one being that it's a random sample, okay, and the second being that n is 30 or more. Those two are the biggies. There is some value in the idea that each sample has independence within it. We'll talk more about that as a group, but that gets referenced as 10n is less than capital N, meaning you're just taking, in this case, your sample is less than 10% of the entire population, which can be important because if your sample's too big, then you start to get individuals that could influence each other, and then it's not completely random and so on. So what we're going to focus on is this to start. These two conditions, if you will, to ensure that our central limit theorem is appropriate. So for the SRS, this would typically be stated in the question, and we just quote it to say, yeah, it's a random sample. The question tells us it's a random sample. Here you would reference and say, well, n equals 55, which is greater than 30. So central limit theorem ensures roughly normal. Okay, and this is what's called verifying a condition or an assumption. And the reason we're verifying is just to show that our information is valid and to show that we know why it's valid. We know this is valid because, and then we'd say because the question tells us that it's a random sample and because of the sample being 55, which is big enough. Okay, so let's end with just an example here. Distribution of home values in our district is skewed to the right with a mean of 600,000. So let's say the mean is right here at 600,000 and a standard deviation of 175,000. So again, what this is saying is mu equals 600K and sigma equals 175K. Again, these are mu and sigma because this is talking about all homes in our district. It's not saying 30 selected randomly homes. So then it asks us to describe the distribution of a random sample of 30 homes. And so what we're talking about here is describing the sampling distribution of a bunch of random samples of 30. Okay, and so what we are going to do here is look at center, shape, and spread. Okay, and this is worded poorly here, but let's assume that this is describe the sampling distribution of samples of size 30, random samples of size 30. Random samples of size 30. Okay, so the center here would be the mu of the x bars equals mu. Okay, so again, mu here was 600,000. The mu of the x bars is the center of the sampling distribution. So that is 600,000. Okay, and that's all we need to write there. We have the notation and we have the value. The shape here, we would denote that n equals 30, which is greater than or equal to 30. So central limit theorem ensures roughly normal. Okay, so that part is taken care of, the shape by the central limit theorem. And then finally for the spread, we get back to the notation again and the sigma of the x bars, which is the spread of the sampling distribution. Again, the subscript of x bar suggests that this is a sampling distribution because it's the spread of all the x bars that we got in our millions of samples, equals sigma over root n, which in this case, sigma was 175,000, and our sample size was 30. So when you take 175,000 and divide it by the square root of 30, you get an answer of about $31,950.48. So what we are saying is the spread of this distribution is 175,000, the distribution up top. But if we were to overlay a sampling distribution right there, the spread of the blue distribution is about $32,000, as opposed to the spread of the red, which was about $175,000. So that's the 175,000 there. Okay, so the calculation here that could go with this is something like this. If we take that same distribution, same scenario, and we said calculate the probability that a random sample of 30 homes would have an average value of over 700,000. Okay, so what this is really saying is what's the probability that x bar is greater than 700,000? Well, previously we had the formula x minus mu over sigma, if this were normal. Okay, now in a sampling distribution, instead of x, it's x bar. Instead of mu, it's mu of the x bars. And instead of sigma, it's sigma of the x bars, which is the same as saying x bar minus mu over sigma divided by root n, if you want to write it like that. So we run the calculation. Z equals 700,000 minus the mu of the x bars, which is the same as mu of 600,000, divided by the sigma, which is 175,000 over root n. Okay, so that's statistic minus parameter of the mean divided by the standard deviation. So we get that z-score. Okay, so what we have here is we get that $100,000 is the numerator, and we divide that by the value that we got when we did the sigma over root n, which was the about 31,950, 48. And you don't need to write this step necessarily, but that gives us a z-score of about 3.13. What that means is in our sampling distribution, in order to get $100,000 over our mean, which is what we did here, 700,000 minus 600,000, with the sampling distribution having that spread of about 32,000, we are saying that on our sampling distribution, which was centered here at 600K, and again, we have now a standard deviation is about 32,000 away, so this is about 632K, 664K, and 696K. Well, we're way out here, and so we are trying to find the probability that Z is greater than 3.13. Now again, what happened here is because we're talking about 30 homes, it's much less likely that an average of 30 homes would be this much over the mean. To find a single home that's this much over the mean would not be rare at all, okay? But now we're talking 30 homes at a time, and so you might have some very expensive homes in there, but you're also going to have some $300,000 or $400,000 homes in there as well, so it would be much less likely for us to actually get this many homes, 30 homes, to have an average home value that's $700,000 or more. At this point, we can do that normal CDF function again, which was second vars on your calculator. Normal CDF, the lower bound here is going to be the 3.13, okay, because this is from here over, this is a z-score of 3.13, 3.13 and over, and the upper bound can be some big number like 99. And that will give us what the likelihood is of getting a probability this, or getting a home value average this high, which is about 0.00087. In other words, extremely unlikely, tenths, hundreds, thousands, 10,000s, 100,000s. If we took 100,000 samples of 30, we'd only get 87 out of 100,000 that would be this much over the mean. So pretty rare for us to get an average of 700,000. As you can expect, most of our averages will be somewhere in that 570 to 630,000 range in terms of the averages. But again, this is just a follow-up on our previous unit in terms of the calculation for the Z. It's just that now we're talking about more than one at a time. Okay, this technically was over root 1 last unit, and now it's over root n. And so that's the only difference, because n here was 1, now n is greater than 1. So that's the probability calculation. And then finally, there's just some connections here to business statistics. The business stats for dummies, there's a link here that showed up in Investopedia. Sampling distributions show up. I'll leave it at that for now. Thank you again for listening. And as always, if you have any questions, please ask.